infinite series. One of the most famous and important of all diverging series is the harmonic series. And the harmonic series is a sum as k goes from 1 to infinity of 1 over k, which is 1 plus 1/2 plus 1/3, and so on. This series arises in connection with the overtones produced by a vibrating musical string, for example. And it's not clearly evident that this series diverges. So the way we're going to show that it diverges is by looking at the sequence of partial sums, and we're going to show that it's unbounded. So if you look at your partial sums, you get that s sub 1 is equal to 1, s sub 2 is 1 plus 1/2, s sub 3 is 1 plus 1/2 plus 1/3, and so on. And clearly, since we're adding a positive number each time, we know that this is an increasing sequence. So by our theorem, we can prove divergence by demonstrating that there is no constant m that is greater than or equal to every partial sum. So to do this, we're going to consider some selected partial sums, namely the ones s sub 2, s sub 4, s sub 8, s sub 16, and so forth, where the subscripts are successive powers of 2. So the partial sums will be s sub 2 to the n. Now let's look at some of those partial sums. S sub 2 is equal to 1 plus 1/2. And since 1 is greater than 1/2, we can say that s sub 2 is greater than 1/2 plus 1/2, which is 2 over 2. Now if we go to s sub 2 squared, that's going to be equal to s sub 2 plus the remaining terms, which is plus 1/3 plus 1/4. And since 1/3 is clearly bigger than 1/4, we can say that this in turn is greater than s sub 2 plus 1/4 plus 1/4. So since s sub 2 is greater than 2 over 2, this turns this inequality to s sub 2 to the 2 is greater than 3/2. Now we can continue this for s sub 2 to the 3rd. And if we keep doing that, we'll see that s sub 2 to the n is greater than n plus 1 over 2. Now, since for any m that we choose, we can find an n such that n plus 1 over 2 is greater than m, we know our sequence is unbounded. Therefore, we know that our harmonic series, given by this formula, diverges. So here's a theorem that will come in really useful. It says that if my series converges, then the limit of my terms has to go to 0. Now you have to be really careful with this theorem because the converse isn't true. You cannot say if the limit of my terms goes to 0, then my series converges, because we know that's not true. We saw an example with our harmonic series. So be careful you don't go backwards with this one. And from that theorem, we come up with the most important test, which is called the nth term test for divergence. And this theorem says if the limit as k goes to infinity of our use of k doesn't equal 0, then our series diverges. And this can be a quick and easy test anytime. So for example, let's consider the series k equals 1 to infinity of k divided by k plus 1, which is 1/2 plus 2/3 plus 3/4, and so forth. This diverges because the limit of the terms k over k plus 1, well, this is a rational function in terms of k. The limit's going to be equal to the ratio of your leading coefficients. This limit's equal to 1, which doesn't equal 0. So by the nth term test for divergence, we know that the series diverges. Another useful thing is knowing how and when we can combine series. And if you have two series that are convergent, then you can go ahead and add them together by adding the terms together, or subtract them by subtracting the terms. And the way we will say this is that the sum of the series given by u sub k plus v sub k is equal to the sum of the series u sub k plus the series v sub k, and the same thing for our differences. Now, if our u sub k and v sub k's aren't convergent, then we cannot say this. Another thing we can say is that if c is a non-zero constant, then this series and this series both converge or both diverge. If they converge, then we can say that the sum of the series c times u sub k is equal to c times the series u sub k. Another useful thing is that convergence or divergence is unaffected by deleting a finite number of terms from the beginning of the series. So what this means is that for any positive integer k, no matter how big or small, the series k equals 1 to infinity of my u sub k's, and the series k starting at capital K to infinity of my u sub k's, both converge or both diverge. So let's look at an example. Looking at this series, I can see this as the series 3 over 4 to the k minus the series 2 over 5 to the k minus 1. And when I write it this way, you can see the first part is a geometric series with a equal to 3/4 and r equal to 1/4. And the second one is a geometric series with a equal to 2 and r equal to 1/5. So, since the r's in both cases are less than 1, we know that they converge. We know that their sums are given by this formula. And when we simplify, we find that our new series up here converges and has a sum of -3/2. In this example, let's look at the sum as k goes from 1 to infinity of 5 over k. Well, I can rewrite this in here as 5 times 1 over k. So this is a constant times the series. If I pull the 5 outside, I get 5 times this series 1 over k. Now, since this right here is the divergent harmonic series, we know that our original series diverges as well. Now if we look at the sum as k goes from 10,000 to infinity of 1 over k, well, this is just my infinite series with the first, 9,999 terms chopped off, so we know this series diverges since our harmonic series diverges. Here's another theorem that comes in very useful. If the sum of my u sub k is a series with positive terms, and if this sequence of partial sums is bounded, then the series converges. Otherwise, the series diverges.